Uh, Hello, everyone. Welcome to the 87th online Spintronics seminar. It is my great pleasure to introduce today's speaker, Dr. Felix Büttner. Felix received his PhD in 2013 from University of Mainz, where he worked under the joint supervision of Professors Matthias Clauy and Stefan Eisebit. His topic was the time-resolved imaging of the gyrotropic motion of a room temperature skyrmion. After a short period in industry, he then joined the group of Professor Jeffrey Beach at MIT. There he focused on the physical limits of size and speed of room temperature magnetic skyrmions. He's a recipient of the Best Young Researcher Award of the IEEE Italy and IEEE Magnetic Society. Since 2020, he's an independent young investigator at Helmholtz Zentrum, Berlin, where he aims at imaging magnetic textures with ultimate spatial and temporal resolution. So without further ado, Felix, you have the floor.
Okay, thank you very much, Jen, and Kirill, thank you very much for inviting me to this very nice seminar here. So the work I'm going to present has been conducted mostly in my time at MIT in the group of Jeff Beach, and some of it at my new affiliation at Helmholtz Zentrum in Berlin. So today we're going to focus on surprising insights from fluctuating magnetic textures. So we are going to look at topological phase transitions and a new form of pinning. So this topic is generally centered in the field of magnetic skyrmions and skyrmion materials, where a magnetic skyrmion is depicted here. It's a spin texture where you have a spin in the center, which is pointing in the down direction, and then usually in our images, it appears as black. And this is embedded in a matrix of spins that are pointing up. And this is these up-pointing spins are then depicted as white in our images. And there's a continuous rotation between these areas, and this gives skyrmion a particular topology. So that skyrmion is topologically different from a uniform magnetic ground state. And these skyrmions have a wealth of applications, possible applications, as you can or have heard in the talk of Matthias Clauy last week. So I will not go into very much detail of applications of magnetic skyrmions, but today really focus on a fundamental question, a fundamental physical question, namely the nucleation of magnetic skyrmions. How can this proceed? So if the skyrmion is topologically different from the uniform magnetic state, how can we then switch from a uniform magnetic state to a state that has skyrmions, and even a large number of skyrmions? And so in this process here, illustrated here, we are actually changing the global topological charge of the system. So that is what we call a topological phase transition, a transition from a trivial topological state to a state that has a net topological charge. So the first part of this talk will focus on how this transition can actually happen. So the skyrmion being a topological object doesn't mean it's fundamentally completely protected. So like topology is not a conserved quantity in nature. It can actually change when you transition through a singular point of the system. So a singular point in a skyrmion system would be if you change the skyrmion diameter down to a diameter of 0. And so it boils down in the end to a question of energy and energy barriers. And so the energy of a skyrmion as a function of its diameter is then shown here. It's something you can calculate analytically, as shown in this paper. And what is remarkable here is that there is actually an energy barrier between this ferromagnetic state at r equals 0, or at 0 diameter, marked here at 0, 0, and the skyrmion state depicted here, which is resting in this energy minimum. So there is a significant energy barrier here. And for a typical material of a ferromagnetic multilayer, for example, of 15 repeats of platinum, cobalt, platinum, coffee, B, and GO, for example, this energy barrier here can exceed several hundreds of kT at room temperature. And this energy actually has a topological origin. So the energy you need to overcome to change from a uniform magnetic state to a skyrmion state is of topological origin and has a value of several hundred kT. So in fact, then we would expect that this transition, while being possible in general, is strongly first order. It's something that we wouldn't expect to happen spontaneously, at least at room temperature or anywhere near room temperature, because of this very large energy barrier. So, and in fact, experiments in the past have shown that switching is a gradual and defect-driven process. So, for example, in this paper by the group of Christian Bach, they have observed that the decay, so the reverse process where you annihilate skyrmions, is a strongly Arrhenius or an Arrhenius process, Arrhenius-driven decay process. And on the same time, we have also observed the nucleation of magnetic skyrmions by spin orbital current pulses. So the experiment is depicted here. So we have a magnetic track, and in this track we focus with our microscope on this circular field of view. Okay, then we are injecting current pulses. And initially, this system here is saturated, and after the injection of current pulses, we observe magnetic skyrmions here. And then what we did is we repeated this experiment over and over again, and we then plotted the probability of finding a skyrmion in a particular pixel of this circular field of view. And what we see here is that there is a very highly concentrated probability distribution in some areas here. So if we evaluate this, we can quantify it with this number variance of a mean of this distribution of finding skyrmions in particular positions. And this number is relatively large. So this is a process that is clearly defect driven. So what is similar to what we expect in other first order phase transitions. Imagine, for example, the freezing of water. Water can only freeze if you have defects in the water. If you have very pure water, you can cool it to below negative 20 degrees Celsius, and it wouldn't freeze because for this first order phase transition to happen, you need to have defects at which you can overcome the energy barrier. So having this in mind, we were very surprised in 2018 to read two papers from Spintech and from EPFL, where the people reported that you can actually nucleate magnetic skyrmions with single femtosecond laser pulses, and not only one skyrmion, but a whole pattern of a whole array of magnetic skyrmions by just one very ultra-fast excitation. So we actually then reproduce this experiment in our own material system, what we then did is to perform a systematic study to understand how this kind of process can be understood. So how the switching can actually happen on such a short time scale. So we started this systematic study exploring these 5 items, which I'm going to explain in the next slides. So the first one is we were looking at we were confirming that what we're nucleating with the laser are actually skyrmions. And so we did measurements of the skyrmion Hall effect and Lorentz transmission electron microscopy. And in both cases, we found that all of the textures are indeed skyrmions. 100% of the textures we've been nucleating with the laser pulses are skyrmions. The next experiment we did was to investigate the fluence dependence of the process. So here is shown the fluence on the x-axis and the number of laser pulses on the y-axis, and the resulting state here in the color. So what we find is that above a certain very sharp fluence threshold, we only need a single pulse to nucleate a pure skyrmion state. Whereas below that threshold, we need at least 10 to the 4 pulses to produce the same result. So below the threshold, apparently, it's an activation of an energy barrier, a stochastic process, whereas above the threshold, it's more like a phase transition. So there's a signature of a phase transition. Then we also did the same analysis of statistical distribution as we did for the spin orbital nucleated skyrmions. And what we find here is that the laser nucleated skyrmions are very homogeneously distributed. So in terms of numbers, we find that the variance over mean is a value of 1.6, much smaller than the variance over mean in the same material nucleated by spin orbitals. And it's really approaching the value of 1, which you expect from a pure shot noise distribution. So even if even if the distribution is probability distribution is completely homogeneous, just by Poisson statistics, you would expect a variance of a mean of 1. So you would expect some kind of variation. Okay, so this mechanism is apparently intrinsic, and it already indicates that we have a second order, not a first order phase transition. So now, really understanding what is happening, we need to look at the transient state. And for that, we went to the European free electron laser source, one of the most sophisticated instruments you can work on as a scientist. And here we can really follow the dynamics in space, in reciprocal space and time. So what we did is so-called small angle X-ray scattering experiments. So we're exposing our magnetic film with X-ray pulses, and we're recording the scattering pattern in the far field. And this far field scattering is essentially the Fourier transform of our magnetization distribution in our sample. So the higher the scattering angle, or higher signal, the higher the signal, the higher scattering angles, the shorter the length scale of magnetic correlations in the system. And so we are recording now 3 images or scattering patterns, one before the laser pulse when the sample is saturated, one long after our laser pulse when the skyrmion has gone to the static skyrmion state to confirm that we really went into the skyrmion state. And then the main experiment is this transient state here, which is recorded just after the infrared laser pulse. So here's an example of the 3 scattering patterns that we observe. The first image here is showing that we see essentially nothing before the laser pulse arrives, confirming that there's no magnetic texture or no texture at all in the system before the laser pulse. Then after the laser pulse, long after the laser pulse, we see the clear scattering ring, which we independently then also confirm corresponds to the skyrmion state. And then, interestingly, in between, at very short time scales of a few hundred picoseconds, around 100 picoseconds, it starts to appear this kind of cloudy, like broadly distributed distribution of scattering, all the way up to very high scattering angles. And this is really showing us that on very short time scales, we have a distribution of all different length scales in the system. And this is what we call a transient fluctuation state. Now, how does this transient fluctuation state really relate to the formation of skyrmions? To answer this question, we collaborated with the group of Bertrand Dupé and Rairosinova in the University of Mainz. And they actually, even before we started collaborating with them, they predicted that statically, by Monte Carlo simulations, they predicted that in interfacial DMI materials, you have at low temperatures, so this is a temperature, this is a magnetic field here. At low temperatures, you have static magnetic phases. At high temperatures above TC, you have the paramagnetic phase. And then in between, you have a disordered skyrmion phase. So these are static simulations, so no information about the time correlations of these skyrmions, but they already predicted that the spatial arrangement of these skyrmions is very inhomogeneous and random. So now, interestingly, in the context of our collaboration, they performed time resolved at spin dynamics simulations. And starting here, so this is the time scale, time on the x-axis, starting with a temperature in the static phase, they heated, or in the simulations, heated the system to this intermediate phase and then cooled back down. And interestingly, what they find is that as soon as you cross the threshold, the temperature threshold to the intermediate phase, there is a topological charge building up. So you're nucleating skyrmions without the skyrmion counterpart very rapidly in this, as soon as you enter this intermediate state. And as you cool back down, these skyrmions remain stable. So this is really what we also observed in the experiment, right? So, but the simulations actually can tell us something about the mechanism. Specifically, they tell us that as we approach the Curie temperature from below, like we are still below the Curie temperature, but we are approaching it, we are reducing the effective exchange energy. And so this is a strong energy in the system. So naturally, we can also assume we didn't do, or they didn't do simulations of multilayers because computationally too complex. but we can reasonably assume that if the exchange energy is going down, that also the coupling between the layers, which is much weaker, is also going down. So in that sense, we are actually reducing the effective film thickness from 15 layers to just 1 layer. So we're reducing the film thickness T. And since the topological energy barrier is proportional to the product of the exchange constant and the film thickness, this product is really drastically going down. So what is really happening here is, instead of the need of going over this energy barrier here by thermal activation, instead we are reducing the energy barrier due to this thermal fluctuations. And then we can very easily go from the ferromagnetic state to the skyrmion state. So why do we believe these simulations? Because they agree with the experiment in 4 key areas. First of all, if with a Fourier-spaced evolution. So this is the Fourier-spaced evolution recorded in the XFEL experiment. And this is the evolution we obtained from the simulations. They have different timescales because of simplifications of the model, but otherwise they look qualitatively very, very similar. Secondly, we have 100% skyrmions and no anti-skyrmions in the final state in both the simulations and in the experiment. We have a clear fluent threshold. So in the simulations, we need to reach the intermediate state. Otherwise, we do not see any skyrmion nucleation. And the mechanism is intrinsic. So no defects are needed, especially in the simulations. The simulation is completely homogeneous. There's no defects involved. So regarding the question of how fast, so this is something we answer by looking again at the experimental data. You cannot extract from the theory. And here we know that from the interpretation of the switching mechanism, we know that the ultimate time scale when switching needs to finish is when all these layers have coupled again ferromagnetically. When there is coupling between the layers, there is no more switching. And this switching we can observe from the total intensity, total scattered intensity, when it approaches the final value. And this is happening after 300 picoseconds in our experiment. So after 300 picoseconds, we get full scattering. Full scattering means that all the layers have coupled again, that there's a uniform magnetization across all the layers. And so we can conclude that the topological switching has completed in 300 picoseconds or less. And just to compare as a remark, this heat-induced topological switching is not limited to this picosecond timescale. It can proceed on a picosecond timescale, but it can also proceed if you are heating the system slower. Or faster. So in this case here, this is actually showing that the switching can also happen in single layers, not only in multilayers. And then regarding the timescale, we compare to different experiments. For example, this experiment here is showing skyrmion nucleation by Joule heating with a current pulse, nanosecond current pulses through the magnetic material. This experiment here is showing skyrmion nucleation by Joule heating of a track next to the skyrmion material. And this experiment here was even done much slower. So by static heating of a sample in transmission electron microscope, the authors found that you can heat the system above a certain critical temperature when you don't see any contrast anymore in the system. But when you cool down from that, what they call, so they call this here the apparent Curie temperature, and here they don't know what this regime actually is. And we believe that this is a topological fluctuation state. When they cool back from that state, they get a very high density of skyrmions. So now the question is, like all these images that are shown here look very nice, but they are obtained quasi-statically. So as shown here, it's before the pulse, after the pulse. There's no imaging happening, or no imaging so far available for what is happening in between. So the question is really, how can we, can we even image the fluctuations? And if so, how can we image them? And the answer is yes. And this is what I want to illustrate in this second part. So first of all, there is, let me illustrate the dilemma. So imagine you go with your smartphone camera to a highway bridge in the night, and you want to take images of passing cars. You will find that there is a fundamental problem Namely, your camera sensitivity is not high enough to capture the individual cause. Either you need to integrate for a long time, as shown in this picture, where you unfortunately lose temporal resolution to resolve this cause, or you go to a very low exposure time and then you just see a black image, you don't see any contrast anymore. And so there's a fundamental dilemma between this temporal resolution and, you can say, contrast or spatial resolution. And so in this case, we cannot resolve the individual cause. They're too fast and too dim. There is a way of obtaining faster images, and that is so-called stroboscopic imaging. This illustrated in this GIF animation here. So even with a slow camera, if you tune the rate of the update rate of your camera exactly to the dynamics or the periodicity of the dynamics in your system, you can actually capture quasi-static or capture the dynamics. However, this only works if the dynamics is perfectly reproducible. If you can sync your recording to the dynamics. And it's something we actually did in the past. We have recorded these real-time videos of magnetic skyrmions. This video is shown here. It's a video that is 15 nanosecond long and is showing this magnetic skyrmion here gyrating after we excited it with the magnetic field pulse. However, to record this video, we had to repeat the same dynamics 100 billion times. So you can easily imagine this is not a technique that works for imaging fluctuations, which differ every time you excite the system. So what can we do about that? First of all, why are we so interested in these fluctuation states? It's not only because of the example that I showed before, but it's very generally interesting in the field of magnetism and much beyond. So, for example, in magnetism, we have stochastic processes in the magnetization reversal if you are nucleating and propagating domains. So the propagation of magnetic domain walls and skyrmions is usually, with very few exceptions, is stochastic, and especially at the nanometer scale. This might be deterministic on if you look at Kerr microscope images, because they have relatively broad spatial resolution. But if you look at the nanometer scale, things become stochastic, and especially if you go to the creep regime. And there's Brownian motion. Naturally, it's a stochastic process. And then there's also very interesting dynamics happening in spin ice systems, or generally in frustrated systems, which are currently not resolvable. So how can we approach this? If we now want to image these kind of fluctuations, what is our approach? So here we start with a technique called X-ray holography. It's a coherent X-ray imaging technique. We expose our samples with a coherent X-ray beam, and then we define a small aperture and an otherwise opaque film on the backside of the sample, so that the X-rays only penetrate through this circular aperture, which is then defining our field of view. Then there's another hole here, which is defining a reference beam, and then we are recording. So the transmitted photons here really encode the information, the magnetic information. And then these photons propagate in free space to our camera detector here. So we have no more lenses or anything in between here. We are directly recording the photons as they propagated to the detector here. And the advantage of this technique, and then we are reconstructing the real space image by numerical reconstruction. So the advantage of this technique is that it's a full field technique. It has very high resolution. We have recently demonstrated we can go down to 5 nanometer resolution in magnetic imaging. It's very efficient because there is no more optics in between the sample and the hologram. So every photon that is transmitted through the sample is also recorded here. And it's very fast. It's actually the only approach so far that has been demonstrated on a free electron laser. So you can even go down to femtosecond resolution. Okay, so now what kind of system do we actually investigate? Our system of fluctuating order is structural state in material, platinum, coffee B, MgO, 15 repeats of that, at a temperature of 310 Kelvin, so just 10 degrees above room temperature. So this material system here has been optimized in the group of Jeff Beach for many years to really study skyrmion dynamics. So it has been optimized for low pin. And so what we find is if we image this kind of material at zero magnetic field, just as a function of time at this slightly elevated temperature, then we see that the domain state evolves naturally just by thermal fluctuations or by thermal hopping. And now we find the dilemma here. So this is a time sequence here of holograms recorded for 5 hours. And in some of these holograms look very nice and crisp, but some of them actually have these domains which are like grayish. So there's apparently some partial contrast in these images. And what we find is, in order to resolve this, if we are making the attempt of going to fewer and fewer acquisitions or to shorter and shorter exposure time, and we eventually find that we are losing too much contrast before losing all contrast before we can actually resolve the dynamics happening here. And let me emphasize that this time scale here of 40 seconds is actually not limited by our camera or the beam line. We actually have had to attenuate the beam in order to not induce any beam-induced motion here. So this is a fundamental time scale that is dictated by the physics of the sample. We cannot go higher because we cannot expose the sample to a higher heat load. So what is the fundamental problem now? Why can we not resolve dynamics that are faster than this 40 seconds that I showed before, which we below this minimum integration time? So the problem is we can record lots and lots of frames on a shorter time scale. But as I said, we need to average them over a lot of these frames in order to get a real space image. Now, if we do not have any information about this magnetic state of the system in these frames, then we have the only choice we have is to average blindly over a fixed duration of time. However, now imagine you would know which frame has which state before you even start averaging. Let's say you color or label these frames. Then it's very easy to just pick the frames that correspond to the same state, regardless of where they are in the sequence, and then only average over those states. And then you can get an arbitrary high statistics and arbitrary good image from this average without sacrificing the temporal resolution. So this is apparently the approach of solving the dilemma between temporal and spatial resolution. So how can we actually label these frames? And the idea is shown here. It's largely oversimplified. So we have in the end a more complex scheme to really get this labeling down to the single frame. But the general idea is that each of these frames here contains already enough information of magnetic state so that you can identify by correlations which of these images here or which of these frames show the same state. So this is a correlation map here. It's showing the correlation between, in this case, 60 different frames. Okay, and what we see here is that for the first 40 or so or 30 or so frames, we have a high correlation, and then suddenly it changes to a low correlation, meaning that the system has remained in one state and then it has changed to a different state. So within that different state, we have again a high correlation, but between this, the frames of this state here and the frames of this state, we have a low correlation. So apparently in this, from this map here, we can already draw a clear line and say, okay, the frames corresponding to the first 30 frames here are labeled state A, blue. States labeled corresponding to the second 30 frames are labeled then yellow. Okay, so this is the general idea. Now, applying this to our data, we actually were able to resolve the full dynamics of our system for these 5 hours, 28,000 frames. And this is just showing here like a brief section of this of the videos that we reconstructed of this fluctuating domain state, just to give you an impression. The temporal sequence of states is then shown here. So we have here the time, here the state number, and we recorded a total of 36 different states. And you see already that there's a vastly different dynamics happening here. Some dynamics are happening very fast, some switching processes. And then at other times, the system remains stable for several tens of minutes. And remarkably, even the same state, in this case, state 3, can be stable from sometimes on a sub-second time scale. So we have sometimes switching between from frame to frame, on this case on a time scale of 300 milliseconds. And sometimes it's stable for 10 minutes or longer. So there's a factor of 1,000 in variation here in lifetime. And this is something that is cannot be explained by Arrhenius process, which requires or predicts an exponential variation of the probability of lifetime. So you have a certain average lifetime, and if you like the probability of finding the system stable for say 10 times, as long as the lifetime is e to the power or 2 to the power of 10 or minus 10. So it's really exponentially suppressed. So it's very very unlikely to find this in an Arrhenius process. The second thing becomes more interesting if we also include the temporal and the correlation information to really construct this so-called state transition network. So what is shown here is all these 36 states, and they are arranged such that their distance approximately corresponds to their correlation value. So the closer these states are, drawn here, the more similar these states are actually in real space. And what we see here is that there is a certain agglomeration of states. So there are certain clouds, as indicated here by the ellipses, and these clouds are characterized by transitions that happen much more predominantly within these agglomerates than between the agglomerates. And this is particularly evident for the ones shown highlighted here with the arrows, so that there is a lot more transitions happening for states within this cloud than between the clouds. And then there's also so-called linker states. So whenever they happen, there is a transition between one of these, this agglomerate, for example, and this agglomerate, it's usually happened through state 6. And while all the other states only link to states to states within the agglomerate. So now to really understand the physics of what is happening here, we then need to look in real space. So what I showed before is in principle something you can also detect with X-ray photocorrelation spectroscopy, but the underlying physics and the mechanism is only accessible by real space imaging. And I would just want to give you a glimpse here, which is showing in this bottom part here. So this is showing the kind of accumulated positions of domain walls that we find in all the states that we observe, like superimposed on top of each other. So there are certain hot spots here where we find very frequently a domain wall, and then there are certain areas where you only find a domain wall once or twice. And then this, I want to highlight this figure here, which is showing then the number of switching events. And evidently, there are some certain areas here where the mechanization never or very seldomly switches. Now, combining this together, we can generate a pinning map. And this is showing two different distinct features. One is we identify points where domain walls merge. So so you can see that these domain walls here, they almost form like strings in a guitar, and at some points they all go together. And this is the point where we identify an attractive pinning cell. By the contrary, we identify these areas where you have very rarely any switching as repulsive pinning areas. And you already see from my language, this is a pinning point here, an attractive pinning point, whereas the repulsive pinning is an area-shaped feature. So there is a conceptual difference between repulsive and attractive pinning. And we can really understand this from the just topology of a domain wall when it is it's a line-shaped object. that is going through a energy landscape. Okay, so now, so in this picture here, the domain wall is depicted with these lines, and then we have minima, and then we have maxima in this energy landscape. And the domain wall, naturally, it wants to go to the minimum of these depressions, and it really doesn't matter how it actually leaves the depression, because the energy is really determined by this lowest point here. So the domain wall is really pinned to the lowest point of the minimum. That's why this point light. Whereas for a elevation, for a hill in the energy landscape, this hill is entirely avoided. Not only the top, but the entire area here is avoided by the domain wall. So that's why attractive and repulsive pinning sites have different actions for a domain wall, which is one-dimensional. Now, this kind of physics can actually explain what we observe. Now, let me illustrate this based on the example of state 3 and its transitions to state 8, 6, and 34. So first, looking at the transition between state 3 and 6, which are the two most important, two most frequently observed states in our experiment. And this image here is showing in pink, where the domain is black in both cases, in state 3 and 6, in white, where it is white in both cases, and then in blue, where it is black in one and white in the other, and in orange here, where it is the reverse. So the areas that have switched are shown in light blue and orange here. So here you can see that in order to change from state 3 to 6, you need to overcome a lot of these repulsive pinning sites. Repulsive pinning sites are shown here in these gray areas, whereas attractive pinning sites are shown as black dots. So if we compare this to state 3 and 34, which is also an interagglomerate transitions, then we see that also here we need to overcome certain repulsive pinning sites, but less of them, right? So a large part of the sample here requires no or little switching over repulsive pinning sites. So that's why this transition is also already happening more frequently. Now, if we look at state 3 and 8, we find that there is no repulsive pinning site separating these two states. So all the changes here are only involving attractive pinning sites, but no repulsive pinning sites. And that is why these states are then belonging to the same agglomerate. That's why we have very frequent transitions between them. And that's why we have less transitions between these states. Okay, so that brings me to the end of my talk. I would like to thank all the collaborators that have contributed to this work, especially Bastian Fau, Stefan Eisebit, and their team at the Max Born Institute in Berlin and the TU Berlin. Jeff Beach, my supervisor at MIT, and his group. Wen Hu and Claudio Mazzoli have been key contributors to this development of the coherent correlation imaging and its interpretation. My student Riccardo Battistelli did the reconstructions, the high resolution reconstructions. Theory support for the fluctuation interpretation of the skyrmion nucleation came from Johan Mentig, Bertrand Dupé, and Jairo Sinova. TEM imaging, also again on the skyrmion nucleation part, was done in the group of Klaus Ropers, University of Göttingen. And the XFEL experiments were really only possible because of enormous support by the local scientists from the SCS beamline of Giuseppe Mercurio and his team, as well as the people have developed this new fancy detector, DSSC detector. And a lot of experiments were also done at DAC beamline P04 and supported by Kai Bakci. So with that, let me come to the summary and the outlook. So I hope I've convinced you that magnetic fluctuations are actually interesting, that they are, because they're ubiquitously present in many systems, they offer unexpected transition paths. For example, the path to nucleate a very large number of magnetic skyrmions in a very short time scale. And they offer deep insights into the intrinsic and extrinsic mechanisms of driving domain walls and skyrmions at the nanometer scale. How can we access fluctuating magnetic states? I've shown you two examples. One is by coherent X-ray scattering at the free electron laser source, where we get information in Fourier space. And then if we want to do real space imaging, we can use this new technique, coherent correlation imaging, which is again depicted here. So what is next? One is, of course, we want to combine these two stories and really directly image the ultrafast dynamics of the skyrmion nucleation. So this concept of coherent correlation imaging is actually the strongest point would be if you apply it to a free electron laser source and then really get movies with single frames at the femtosecond scale. And then from that, we also want to extract the topological torch and how it evolves with time. Okay, with that, thank you very much for your attention. I look forward to your questions.
Thank you very much for the interesting questions. We can use the reactions buttons to thank the speaker. This talk is open for questions. If you have any question in Zoom, please use the raise hand button. And if you're watching this on Twitch, you can type your questions into the chat box and I can read it for you. Oh, we have a first question by Yoshi Muruka. I'm just going to read it to you. Thank you for your wonderful talk. With platinum, cobalt, platinum, Lorentz TEM shows that some skyrmions are up and others are down. Sorry, we have someone drilling next door. And next, J and Berruto papers show only up or down. What causes the difference?
I think I did the mic. So you say we have platinum, cobalt, platinum, and in Berruto's paper, but what did you say? What was?
It shows only up or down.
Shows only up or down.
So the Lorentz TEM shows that's up or others are down.
Sorry, can I talk?
Yeah. Sure. Yeah, go ahead.
So in Lorentz imaging, I see some of the skyrmions are white and the others are black. So it means just rotation direction is different, opposite. So one is up and one is down. But in Berruto's paper and others have only just all of them, the wiring direction is same, constant. So
yeah, because
I want to know why.
Okay, so this is not from Berruto's paper. This is from J et al. This is done by Kerr microscopy. So where you see the out-of-plane magnetization. So here it's essentially an assumption that this is a skyrmion from the fact that the system has DMI and that it shows round textures and has been investigated in the past to show actually magnetic skyrmions. So these images do not show the topology of the skyrmions.
Okay.
Whereas these images here show the in-plane magnetization, and it shows that we have clockwise and counterclockwise textures. So when you see white contrast, actually white outer contrast and a black dot in the middle, I think it's clockwise. I need to look this up again. It's one direction clockwise. Let's call it like this. And when it's black and white on the outside, it's counterclockwise.
Yes.
So there is a difference in chirality here. So it's because the system has no DMI. It actually mostly it has for sure no bulk DMI that would favor one block chirality over the other. So that's why the sense of clockwise or counterclockwise is completely degenerate. So half of these skyrmions are showing like clockwise, the other half is counterclockwise, but all of them are defect free. So they are either black or white. Meaning that they have the same, that they have a unit topological torch.
Yes. Just the distribution I was talking about. Okay.
Yeah.
Thank you.
Great. Do we have other question? Let me ask one about the laser heating effect. So you described that it's mainly due to the reduction of the exchange constant due to heating.
Yes.
And so is that energy barrier only due to exchange? Because your anisotropy can also change, your saturation magnetization can also change, even your DMI is going to change.
right? But the energy barrier here, which is it's essentially the zero radius energy of a magnetic skyrmion, is only determined by the exchange constant and film thickness. So if you do if you write down the analytical expressions for all the energy terms apart from exchange energy actually go to zero when the skyrmion diameter goes to zero. The exchange energy is the only term that remains finite. It remains finite because it has these gradient squared. So if you integrate the gradient squared over a like a finite volume, let's say differently. So the total energy when you decrease the skyrmion size is actually going down for all the other energy terms because the volume of the skyrmion is going down more rapidly than the energy density is increasing. It's increasing a little bit in case of DMI, and even staying constant in case of anisotropy. Right. So the anisotropy term is essentially just scaling with the number of spins that are pointing in a direction that's unfavorable by the anisotropy, so in in-plane direction. So as you make the skyrmion smaller and smaller, the number of spins pointing in in-plane directions gets lower and lower. So eventually at zero radius, zero diameter, the anisotropy goes to zero. The anisotropy energy, the total energy in units of joules. The energy density does not, but the energy in terms of the total energy of the system goes to zero.
I see, that
Whereas
makes sense.
The exchange energy is the only one that remains finite. So that's,
I see.
This is this result of originally derived by Belavin and Polyakov in the 70s. The energy of a topological defect in an exchange system.
I see. Thank you. Do you have other question? See if there's any question on Twitch. Okay, it looks like we're running out of questions for now. We'll have another discussion afterwards. So I think for now, we'll just turn off the live streaming and the recording.